Key concepts of audio transformers. Audio transformers are a type of neural network architecture designed to process and understand audio data. Based on the transformer model, which has been highly successful in natural language processing, NLP, audio transformers apply similar concepts to handle the sequential and temporal nature of audio signals. The self-attention mechanism is a core component of the transformer architecture, which allows the model to weigh the importance of different elements in the input sequence dynamically. This mechanism is essential for capturing dependencies and relationships within the data, regardless of the distance between elements. Here's a detailed explanation of how the self-attention mechanism works and its application in audio processing. Key concepts of self-attention: query, key, and value vectors. For each element in the input sequence, the model computes three vectors: query, q, key, k, and value, v. These vectors are linear transformations of the input embeddings and are used to determine the attention scores. Attention scores. The attention score between two elements in the sequence is calculated as the dot product of their query and key vectors. These scores represent how much focus one element should have on another. Softmax normalization. The attention scores are passed through a softmax function to normalize them into a probability distribution. This ensures that the scores sum up to 1 and can be interpreted as attention weights. Weighted sum. The output for each element is computed as a weighted sum of the value vectors, where the weights are the attention scores. This allows the model to aggregate information from the entire sequence, with more relevant elements having higher weights. Self-attention in audio processing. When applied to audio data, self-attention helps in capturing temporal dependencies and contextual information. Here's how it's typically implemented. Input representation. Audio data is usually represented as sequences of frames, which can be raw audio waveforms or features like MEL spectrograms. Linear transformations. Each frame in the sequence is linearly transformed into query, key, and value vectors. Attention calculation. Attention scores are computed between all pairs of frames, capturing how much each frame should focus on every other frame. Contextual aggregation. The final representation of each frame is obtained by aggregating information from all other frames, weighted by their attention scores. Example calculation. Let's say we have an audio sequence represented by 3 frames. Here's a simplified step-by-step calculation of self-attention. Linear transformations. Compute query, key, and value vectors for each frame. Are weight matrices. Attention scores. Calculate attention scores using dot product. Score. Softmax normalization. Normalize the scores. Benefits of self-attention in audio processing. Capturing long-range dependencies. Self-attention can capture relationships between distant parts of the audio sequence, which is crucial for understanding context and structure. Parallelization. Unlike recurrent neural networks, RNNs, self-attention allows for parallel processing of the sequence, leading to faster training and inference. Flexibility. Self-attention is adaptable to various input lengths and can handle sequences of different sizes without modification. Applications in audio. Speech recognition. Self-attention improves the model's ability to understand and transcribe spoken language by focusing on relevant parts of the audio. Music generation. In music generation, self-attention helps in maintaining the coherence and structure of musical compositions over long sequences. Audio classification. For tasks like genre classification or sound event detection, self-attention enhances the model's ability to discriminate between different sounds by considering the entire context. Conclusion. The self-attention mechanism is a powerful tool in the transformer architecture, enabling models to capture complex dependencies and contextual information in sequential data. Its application in audio processing has led to significant advancements in various tasks, leveraging its ability to dynamically focus on relevant parts of the audio signal. Positional encoding is a crucial component of the transformer architecture, especially for handling sequential data such as text, audio, or time series. Since transformers process input data in parallel and do not inherently understand the order of the sequence, positional encoding is introduced to provide information about the relative positions of the elements in the sequence. Why positional encoding is needed. In traditional recurrent neural networks, RNNs, and long short-term memory, LSTM, networks, The sequential nature of the input is inherently preserved due to their sequential processing. However, transformers process the entire sequence simultaneously, so they require an additional mechanism to encode positional information. How positional encoding works. Positional encoding involves adding a vector to the input embeddings to indicate the position of each element in the sequence. This allows the model to distinguish between different positions and understand the order of the sequence. Mathematical formulation. A common approach to positional encoding, as proposed in the original Transformer paper by Vaswani et al. 2017, uses sine and cosine functions of different frequencies. Is the dimension of the model. Intuition behind sine and cosine functions. The use of sine and cosine functions allows the model to encode positional information in a continuous and periodic manner, providing a unique representation for each position. This method ensures that the positional encodings have the following properties. Uniqueness. Each position in the sequence has a unique positional encoding. Relative positioning. The encoding captures the relative distances between positions, which is useful for understanding dependencies in the sequence. Smooth variation. The use of continuous functions allows the encodings to vary smoothly, which helps in capturing sequential patterns. Example of positional encoding. Consider a sequence of length 5 and a model dimension. Application in audio transformers. In audio transformers, positional encoding helps the model understand the order of audio frames or features over time. This is critical because the temporal structure of audio signals, e.g., phonemes in speech or notes in music, carries significant meaning. Speech recognition. Positional encoding helps the model understand the sequence of phonemes and their temporal relationships, which is crucial for accurate transcription. Music generation. For generating music, positional encoding allows the model to maintain the structure and timing of notes, ensuring coherence in the generated composition. Audio classification. Positional encoding aids in distinguishing between different temporal patterns, improving the accuracy of classifying audio sequences. Conclusion. Positional encoding is an essential technique in transformers that enables the model to capture the order of elements in a sequence. By incorporating positional information into the input embeddings, transformers can effectively process sequential data, leading to significant advancements in tasks like speech recognition, music generation, and audio classification. Multi-head attention is a crucial component of the transformer architecture, enabling the model to attend to different parts of the input sequence in parallel. This mechanism allows the model to capture diverse relationships and dependencies within the data, enhancing its ability to understand and process complex sequences. Key concepts of multi-head attention. Multiple attention heads. Instead of using a single attention mechanism, multi-head attention employs several attention heads. Each head performs a separate attention operation, allowing the model to focus on different parts of the sequence simultaneously. Parallel attention mechanisms. Each attention head operates independently, computing its own set of query, Q, key, K, and value, V, vectors, and producing its own output. These outputs are then concatenated and linearly transformed to produce the final result. How multi-head attention works. Linear projections. For each attention head, the input embeddings are linearly projected into query, key, and value vectors using separate weight matrices. Each head computes attention scores using the scaled dot product attention mechanism. The scores are scaled by the square root of the dimension of the key vectors. To stabilize gradients. Concatenation and linear transformation. The outputs of all attention heads are concatenated and passed through a final linear transformation to produce the output of the multi-head attention mechanism. Mathematical formulation. For a given input sequence, the multi-head attention mechanism can be described as follows. Linear projections is a weight matrix for the final linear transformation. Benefits of multi-head attention. Capturing diverse relationships. Different attention heads can learn to focus on different parts of the sequence, capturing various relationships and dependencies simultaneously. Improved expressiveness. By combining multiple attention heads, the model can represent more complex patterns and interactions within the data, improving its expressiveness and capability. Robustness and generalization. Multi-head attention helps the model generalize better by distributing the learning across multiple heads, reducing the risk of overfitting to specific patterns. Applications in audio processing. In audio transformers, multi-head attention enhances the model's ability to process and understand audio sequences by capturing diverse temporal and spectral relationships. Speech recognition. Multi-head attention allows the model to focus on different aspects of the speech signal, such as phonemes, intonation, and background noise, leading to more accurate transcription. Music generation. By attending to various elements like melody, harmony, and rhythm, multi-head attention helps generate coherent and musically rich compositions. Audio classification. Multi-head attention improves the classification of audio signals by capturing different characteristics and patterns, such as timbre, pitch, and duration, enhancing the model's ability to discriminate between different classes. Example of multi-head attention. Here's a simplified example in Python demonstrating how multi-head attention can be implemented. Python. Copy code. Import torch. Import torch.nn as nn. Class multi-head attention, nn, module. Def self, number underheads. Super, multi-head attention, self, dot, self dot number underscore heads equals number underscore heads. Self dot equals // number in the threads. Self dot q underscore linear equals nn. Linear, d underscore model, d underscore. Self dot k underscore linear equals nn. Linear, d underscore model, d underscore. Self dot v underscore linear equals nn. Linear, d underscore model, d underscore. Self dot out underscore linear equals nn. Linear, d underscore model, d underscore. Def forward, self, x. Batch underscore size equals x dot size, 0. Hashtag linear projections. Q equals self dot q underscore linear, x dot view, batch underscore size, -1, self dot number underscore heads, self dot underscore. Transpose, 1, 2. K equals self dot k underscore linear, x dot view, batch underscore size, -1, self dot number underscore heads, self dot underscore. Transpose, 1, 2. V equals self dot v underscore linear, x dot view, batch underscore size, -1, self dot number underscore heads, self dot underscore. Transpose, 1, 2. Hashtag scaled dot product attention. Scores equals torch dot matmul, q, k dot transpose, -2, -1, slash torch dot sqrt, torch dot tensor, self dot underscore. Type equals torch dot float 32. Attention underscore weights equals torch dot nn dot functional dot softmax. Scores dim equals -1. Attention underscore output equals torch dot matmul. Attention hashtag concatenation and final linear transformation. Attention underscore output equals attention output dot transpose 1, 2 dot contiguous dot view batch underscore size -1 self dot number underscore heads asterisk self. Output equals self dot out underscore linear. Attention of output. Return output. Hashtag example usage. D underscore model equals 512. Number underscore heads equals 8. X equals torch dot rand 64 10. D underscore model. Hashtag batch underscore size. Seek underscore lint. D underscore model. Multi underscore head underscore attention equals multi head attention. D underscore model. Number underscore heads. Output equals multi underscore head underscore attention, x. Print, output dot shape, hashtag expected output shape, 64, 10, 512. Conclusion. Multi-head attention is a powerful mechanism in the transformer architecture, enabling the model to attend to multiple parts of the input sequence in parallel. This capability is particularly beneficial for audio processing tasks, where capturing diverse temporal and spectral relationships is crucial for understanding and generating audio signals. By leveraging multiple attention heads, audio transformers can achieve superior performance in tasks like speech recognition, music generation, and audio classification.